you should all be able to see the title slide of his talk. I am able to.
Let me go just full screen.
Yeah. So before you go ahead, I'm very happy to introduce to the group Professor Amjad Ashoorioon, who is at the Institute for Fundamental Sciences, or the IPM, in Iran. Amjad is a former member of the Astro Group. He was here, I guess, almost 20 years ago and got his PhD in 2007, and I believe you saw his bio in an email. He has done postdoctoral work at University of Michigan and at Uppsala University and at Lancaster University, and he's made interesting contributions to primarily cosmic inflation, but has done a number of quite interesting things along those lines, things in chain inflation, or a new approach he calls M inflation, and also work on black holes. And today he is going to tell us about primordial black holes from the end of inflation. So Amjad, please go ahead.
Thank you very much for the nice introduction, Rob. So as Rob mentioned, my talk will be about primordial black holes from inflation or from the end of inflation. So this is my first, one of my first attempts dealing actually with black holes. So I haven't worked that much, but we are interested in just seeing if we can get the seed for formation of these primordial black holes, which have become of interest since LIGO has observed the signature of merging of two black holes. So as LIGO discovered the signal of merging black holes in the mass range of few tens of solar mass, it occurred to people that what if these black holes are primordial? So one should note that black holes can be astrophysical, and by that I mean they are coming from collapse of stars. And by primordial black holes, I mean they are coming from highly compressed matter or radiation overdensities during the early universe. And the first groups that just raised this issue, one of them is the Kamionkovsky et al., the first one here, the Simon Baer's paper, which proposed that. And another group was the one just led by Sasaki, and both papers appeared around the same time. And this possibility was just had been excluded in the literature, but this group revised their result, and they showed that the inferred merger rate is compatible with having the density of primordial black holes, in that mass region is still to be less than the dark matter energy density. So in contrast to the astrophysical black holes, whose mass should be bigger than about twice of the solar mass, the mass of primordial black holes can be smaller or bigger than the size of the sun, the mass of the sun, but can also be, but they have also to be bigger than the Planck mass in order to be able to neglect the quantum gravity effects for them. Although there are some suggestions by Bernard Carr that the black holes evaporate until their mass become of order of the Planck mass, and then they stop, and then he has proposed them to be also contributors to the dark matter energy density. One suggestion for creating these primordial black holes is given by Hawking, Moss, and Stewart in 1982. And they have shown that when first order phase transition occurs, if enough number of these bubble walls that are created during the phase transition collide in a single region, in a point in a space-time, then the energy density within that region, if is big enough such that it just collapses, then it can lead to creation of black holes. And the mass of these black holes is roughly about would be roughly about m Planck squared over 4h, where h is the Hubble parameter given by that false vacuum energy density that derives the expansion, the accelerated expansion. Using this, Crawford and Schramm in 1982, around the same time, had raised the possibility that if QCD phase transition is first order, that would give rise to black holes of thousands of solar mass, and which can contribute substantially to the dark matter energy density. Another suggestion for creating these primordial black holes is given again by Hawking in 1983 or 4. I don't remember, so the year should be taken with a grain of salt. But so he has proposed that the shrinkage of cosmic string loops that would lead to gamma ray emission, if this shrinkage is just, again, if the energy density of this cosmic string loop is just large and it shrinks, then one can also have black hole formation. And again, from lack of observation of such gamma rays, he concludes that the tension of those cosmic strings should be less than 10 to the power of -6. And this is comparable to the bound European pulsar array timing and Planck put on cosmic strings tension. So it's just an order of magnitude, which is, I mean, I think remarkable. As I said, the idea of just collapse of a large overdensity fluctuation during the early universe is the idea which was originally proposed by Novikov and Zeldovich in 1967. And that would lead to generation of primordial black holes. So one can show that if you want that these large fluctuating amplitudes during radiation domination lead to primordial black holes, the density contrast, rho minus rho bar over rho bar, where rho bar is the mean density of the universe. If that is bigger than a threshold, then this overdensity can, with large amplitude, can collapse and create a primordial black hole. And K here is just, big K is just the curvature of the collapsing region of the region with large fluctuating amplitude, because you can look at it as like a separate universe with a curvature, with a constant curvature. And then that tells you that this can be, should be bigger than a threshold. And noting that fluctuations with densities smaller, with wavelengths smaller than the Jeans length, cannot collapse. That tells you that this density contrast, big delta, should be bigger than CS squared during the radiation domination phase, which is 1/3. So if you calculate the mass, if you want to know the mass of the black holes that would arise from such a collapse of overdensity, you should note that this mass would be proportional to the horizon mass at the time when these large fluctuating amplitudes enter the horizon. And this factor was computed by Bernard Carr in 1975 and turns out to be about 0.2. Um, so if you just compute, if you introduce a variable beta, which is the energy density of the primordial black holes to the total energy density at the time of formation, it's related to the omega dark matter, cold dark matter, and the fraction of PBH against the cold dark matter via this relation. And noting the previous equation that I obtained just relating to the mass of black holes to the Hubble parameter, you can express it in this way. There is also another way to just write down beta, and that is telling you that beta is the probability that an amplitude with fluctuating mode with amplitude larger than the threshold, delta threshold, enters into the horizon. And just write it down as in terms of this integral. So if you assume that your probability distribution is just Gaussian, then the integral could be computed, and it's roughly given by this exponential of minus nu threshold squared over 2. Where a new threshold is just this threshold amplitude delta th over sigma mpbh, where sigma is the variance of the density fluctuations on the mass scale of mpbh. So if you have just the primordial power spectrum, primordial density power spectrum, which is noted here by P delta, then you can calculate the variance sigma via this relation by introducing a smoothing window function, W. And then you can also compute this variance from the integral of the power spectrum smoothened over this window function. And so usually W is taken to be also an exponential, a Gaussian exponential, and R is taken the comoving scale where this fluctuation with large amplitude enters inside the horizon, which can also be expressed in terms of the mass of black hole and also the factor gamma star that I introduced earlier, and also the degrees of freedom during the horizon reentry by this equation. So during the radiation domination era, you can express the mass of the black hole in terms of its wavelength in this manner. And so there are so depending on the mass of the primordial black hole, I mean, you can say at what wavelength you should have this large amplitude, fluctuating large amplitude, such that you obtain the required primordial, the primordial black hole with the required mass. So there are various bounds on the abundance of PBHs. And some of them are, I mean, I'm just not an expert in this area, but this part, I mean, is coming from the fact that, I mean, the very small region black primordial, very small mass primordial black holes, because they can evaporate, they can distort the CMB radiation. So from them, for example, you obtain a bound on the fraction of primordial black holes on their mass. Also from femtolensing, you can also obtain a bound on the number of on the fraction of primordial black holes in between 10 to power of 18, 10 to power of 20 grams, roughly about 10 to power of minus if I 18 to 33 is minus 15 to 10 to power of minus 13. You get some bounds also in this region. From 10 to power of minus 15 to 10 to power of minus 13, you get you don't have that much of bound on the fraction of primordial black holes over the dark matter energy density. So basically in this region, you can have all the dark matter coming from primordial black holes. Also, there are some bounds from some Kepler, also from lensing in by Eros and Mako, and also from the CMB. Also, there is a window in about 10 to 100 solar mass, where dark matter where about 1/10 of dark matter could be coming from primordial black holes. So these are two windows which are still open, and primordial black holes can contribute to the dark matter density in this region
Can I ask
substantially.
something?
Yeah, sure.
Sorry. Is that femto lensing bound coming from like gamma ray bursts? Do you know?
I guess so, yeah. So as I said, I'm not very familiar. I do not know the details that much about these femtolensing and what are the experiments being done. But I mean, this is just a graph you would see in many of these primordial black holes, and these are different experiments and considerations that rule out the masses. But I guess femtolensing is just from such an observation, but I'm not fully sure.
Well, right. Thank you.
Sorry about that.
So the reason why that, the reason why that Subaru constraint dies where it does, comes from just like optics, limiting lensing, right? So just surprised then that the femtolensing at much lower masses has a bound. I suppose if like the observing wavelength is like much shorter.
So on second thought, I think basically PBH evaporation up to 10 to power of 17 grams, that is just coming from the fact that, I mean, if primordial black holes in whatever frequency range is just evaporating, they will distort the CMB distribution, CMB photon distribution. So that is, but femtolensing should be something different. But I don't know. Sorry about that.
Okay.
But I mean, these are for the sake of my talk, I'm just mainly focused on these two mass intervals. 10 to power of minus 17 to 10 to power of minus 13 solar mass, which can constitute the whole just dark matter energy density, and about tens of solar mass to 100 solar mass, where it can be up to 1/10 of dark matter energy density. So we know that inflation is the prime candidate for generating such fluctuations, but the range of scales we have probed with CMB probes, such as WMAP or Planck, is less than 10-fold, or at most about 10-fold. And the amplitude of density perturbation in that region is about 10 to power of minus 9. And it's, I mean, the spectrum is almost flat. It's about, I mean, the spectral index is about 0.965. And with such a low amplitude, with such a small amplitude for curvature perturbations, the probability or the fraction of dark matter which can be coming from primordial black holes is extremely small. It's about exponential of 1 over PR roughly, which is about 10 to power of 8. But we have, as I mentioned, we have only probed very large scales from the largest, from the horizon scale up to orders of 1 megaparsec. And we don't know what has happened to the amplitude of fluctuations, fluctuations coming from the inflation at very small scales. And also, I mean, it's an issue whether we can generate such large fluctuations with inflation at such small scales, if we can just supplement inflation with a mechanism to provide such large enhancement. And if we can, what are the options that we have? As I said, in the window of 10 to 100 solar mass, the PBH can be up to 10% of dark matter. In the window of 10 to power of minus 17 to 10 to power of minus 13, the PBH can be up to 100% of dark matter. And as I mentioned, the mass of the primordial black hole is related to the wave number of the fluctuating mode via this relation. And we know that, I mean, delta n, so delta n of CMB is just the number of E-folds from the time that the largest scale has just come inside our horizon to the time, to the number of E-folds where wave number K has entered inside the horizon. So delta n CMB is just a roughly a logarithm of that, assuming that Hubble parameter is almost constant during inflation. So if you want to generate tens of solar mass primordial black hole, that would mean that you should just enhance the primordial power spectrum at 20 at the scale that exits the horizon, 20 E-folds after the CMBS scales horizon crossing. And if you want to generate primordial black holes in the mass region 10 to power of minus 17 to 10 to power of minus 13, then roughly about 35 to 40 E-folds after the CMB horizon crossing, you should just activate your mechanism of enhancement. The amplitude of curvature fluctuations is given by this expression, h squared over 8 pi m Planck squared over epsilon divided by cs squared. And also there is a fudge factor, modulation factor, gamma s, that I introduce, and I want to just introduce mechanism which introduced the which lead to this enhancement via just creating this gamma s. But I will also go through other mechanisms that can lead to this PBH formation via inflation. One mechanism is through the inflection point inflation, where V prime and V double prime is roughly 0. Remembering that epsilon is V prime over V squared, so that will tell you why that would lead to an enhancement. So basically, if V prime goes to 0, epsilon goes to 0, and if in the region of interest, in the range of scales of interest, if epsilon goes to 0, so the power spectrum of scalar perturbations can get augmented. But there are just some issues, I mean, with how large this mechanism can enhance the amplitude of the power spectrum, especially there are claims in the literature that this mechanism cannot lead to 10 to power to amplitudes larger than 10 to power of minus 4. If you want to satisfy just the constraints of the CMB at larger scales. But I mean, this is, I mean, there are papers that claim that they have models that this mechanism works. So, I mean, this is something that I don't want to get involved in, but I mean, this is just point of conflict and controversy in literature. The other mechanism of enhancing the power spectrum is just by decreasing CS. So we know in dBi inflation and in K inflation, you can usually make CS smaller than 1. And this mechanism was introduced by this group, Gian Massimo Tassinato and Susha Parameswaran and Ivan Zavala and Oshoy. I don't know if the first one is pronounced correctly. If you want to enhance the amplitude of the power spectrum from the CMB scales, then you would need about CS of order 10 to power of -3. But such a CS is in conflict with the effective field theory bound, because that would lead to large FNL, and that would tell you that interacting Lagrangian at the third order would be comparable to the power spectrum itself, and that would invalidate the computations. So this is something that, I mean, again, I would say has difficult time. Something that me and Ghazal and Tony Kim noticed is that one can enhance the amplitude of density perturbation if, for example, in a 6-order dispersion relation like this one, if the quartic term has a negative coefficient, and if some constraints on beta and alpha are satisfied, then it can be, I mean, this can be hugely, the amplitude of density perturbation can be hugely enhanced. And so later, along with Ghazal and Tony and some other collaborators, Roberto Casadio and Michele Ciccoli, we decided to embed this in a more fundamental framework that is extended effective field theory of inflation, which is a way to describe all single field inflationary scenarios. In this scenario, you go to unitary gauge where fluctuations of the inflaton are 0. Therefore, you break the time diffeomorphism. Your metric will acquire another another longitudinal degree of freedom. So it will have 3 degrees of freedom. And but still you have kept the spatial diffeomorphism, and you can introduce all the variables that respect the spatial diffeomorphism and write down an action in terms of those variables. Those are G00, the extrinsic curvature of the spatial hypersurfaces, and the just covariant derivative, and also, I mean, in general, the coefficients that you would be able to construct from the operators are functions of time. But then you can recover this longitudinal component by the Stuckelberg trick that I will not get into. And then you can just find out the action for this pion. I mean, Weinberg was just giving a talk just an hour ago or half an hour ago about the effective field theory and how the Lagrangian for pions have led him to just discover the standard model and things like that. So this is the way backward. So from knowing just the action for the inflaton, we are trying to write down the action for the perturbations, the inflaton. So so this formalism was quite old actually, and it's about 10 years. It was already 10 years old when we realized this issue. That people had tried to just find dispersion relation up to the quartic order. And this was done by Chung, Senatore, and Jared Kaplan, and some other people also involved that I don't remember. But they had excluded the appearance of the 6-order dispersion relation, saying that if such thing happened, then the interacting interacting Lagrangian will become comparable with the just with the leading order Lagrangian, and therefore they had excluded such dispersion relation, the embedding of such a dispersion relation within the effective field theory scenario. But their assumption was that this k to power of 6 just lasts until horizon crossing. But in an expanding background, this is not something that is necessarily true. So basically, once you have a dispersion relation, k to power of 6 is just dominant at very very small physical just wavelengths or large physical momenta. And then as you redshift to just towards smaller momenta, then the contribution and the importance of that term can become negligible. And basically, you can tune your parameters such that you are just dominant by k to power of 4 or k squared term at horizon crossing. So that was what led me, Ghazal, and Tony, and others, Casadio and Ciccoli, to just supplement the effective field theory of inflation with operators with mass scales higher than 2 that was already considered by effective field theory guys, and lay down the framework for the extended effective field theory of inflation, where now 6th order dispersion relation in the for the fluctuations of the inflaton are allowed. So the way we embedded it is just assuming that there are a nabla of the extrinsic curvature square terms also in the unitary gauge action that I showed here, S. And then we just, so the black terms were the term that existed in the effective field theory of inflation, and these mass dimension 3 and 4 operators are the new operators we added in the extended formalism. And with this 6th order dispersion relation, in the cases where alpha and beta are positive, we showed that the general effect on the power spectrum is usually suppressive. So the smaller alpha knots is, the less amount of suppression you get. But when the quartic term in the dispersion relation can come up with a negative coefficient, and the 6th order coefficient is positive, the mode can go through, while still inside the horizon physically, the physical wavelength of the mode is inside the horizon. It goes through some instabilities that enhance the amplitude of the fluctuation, the correlations. So especially we notice that if beta 0 is less than alpha 0 squared is less than 4, we would get just a huge amount of enhancement. So this figure on left is just for alpha 0 squared over 5. So we would get enhancements of order few thousand. But if you remain in this region, the enhancement will be not that much. Of course, it's always bigger than 1. But you would reach about maximum of 14 or 15 for gamma S, the modulation factor. So this was inspiring to me to see if one can reduce this ratio. So as I said here, beta, if it's less than alpha 0 squared over 4. So here we plotted it for alpha 0 squared over 5, and we noticed we reached enhancements of order few thousand. I thought if we go to smaller ratios, one would be able maybe to see this in larger enhancements. And this is what took me and Abbas Al-Rostami and Javad Taqizadeh Firuzjahi to see if we can create primordial black holes this way. And because we needed enhancement in the power spectrum at some specific scales, we used the time dependence in the dispersion relation, the coefficients, time dependence of the coefficients in the unitary gauge action, which would lead to time dependence in the dispersion relation. So basically, I assume that in this formalism that, I mean, we tuned the parameters such that CS squared is roughly very close to 1. So basically, it's basically 1. But alpha parameter at CMB scales is quite small and positive, but around the scales of interest, and by around, I will tell you what I mean by around, it swings down to negative values, and then for a sufficient number of e-folds, which is dictated by how much primordial black holes you would need, it remains negative and then becomes positive again. So here I tried it. I mean, we tried it for the value of alpha 0. So the absolute value of alpha 0 is being about 100. And beta 0 over alpha 0 squared is about 1 over 7.5, so 2/15. And I've assumed that CS squared is 1. So we noticed that with about 2 to 3 folds of delay, we would see this enhancement in the power spectrum. And this you can just tune this window such that it just coincides with the region of the mass region that you want to create primordial black holes with such masses. So still, we wanted to make sure that effective field theory, extended effective field theory of inflation is a sane formalism, and by that I mean that the interacting operator at third order is negligible to the second order. And by noting that zeta can be, so the curvature perturbation can be expanded in terms of the Gaussian just perturbation in this way, and where FNL is an just non-Gaussianity parameter. Subdominance of the second term with respect to the third term will tell you that FNL times zeta should be less than 1, and noting that on the scales of interest for us, zeta is of order of 10 to the power of -1. That will tell us that we have to make sure that FNL is about less than 10. So Tony especially did a great job computing the unitary gauge action up to the third order. And this is something that me, Fazal, and Tony are working on. And the most dangerous operators, I mean, noting how the energy scaling of the operator that you can read off from how omega scales with K. You can note that how T and these operators, T and K, just make a scaling, become scaled, and how pi transforms under this energy scaling, which tells you that if this dispersion relation is 6th order, pi remains scale invariant. So the most dangerous operators are these two operators, di pi squared, time di squared pi. And the second operator is pi dot di pi squared term. But these operators are coming with this coefficient, which is proportional to the coefficients in the just unitary gauge action. And the reason that I say these are dangerous operators because they have negative dimensions, and these operators can become, I mean, they become dominant at horizon crossing. But if I tune these coefficients such that these coefficients appear with 0, I mean, coefficients in the interacting Lagrangian, basically, if you tune the parameters this way, I mean, you can basically I mean, a third order, like just regular inflation, the third order would be at most, I mean, FNL would be at most, would be of order of FNL that would come from the case where CS squared is 1. So basically, you would at most get FNL of order epsilon. If these constraints, if you are not happy with these constraints to be imposed on your theory, you can compute FNL. And in general, so FNL is given by these expressions. And again, you can always tune your parameters. First of all, you would get a suppressing factor of gamma s squared, where gamma s is just the amount of enhancement in the primordial power spectrum. So first of all, you would get a gamma, if gamma s is of order of 10 to the power of 8, you already get a suppression of 10 to the power of 18. But if these are large, if this shape function f, which depends on the 3 momenta, is large, then you still have to satisfy this constraint. And for this range of scales, you would get, I mean, FNL has to satisfy this constraint to be less than 10. And with the large number of parameters that you have in the extended effective field theory, you can always achieve that. So this brings me to the first part of my talk, and I will just talk about another work in preparation. So as I mentioned, if phase transition happens, the collision of bubble walls can just give rise to primordial black holes. So we are contemplating a scenario in which this first order phase transition happens at the end of inflation. So basically, the exit from inflation or a bit after inflation happens via slow roll inflation. So we have a constant in the potential for inflation, we have a constant term. We have a potential for this rolling direction, phi. And we have an interacting term between two fields, phi and psi. And so up to some point, so while your inflaton is rolling, the minima that your inflaton is rolling along is just the only minima. So this would be the picture, the profile, the psi equals to the phi equals to constant values when phi is bigger than some threshold value or some inflection value. Then it reaches an inflection point, so it starts to develop another minimum, and gradually as phi decreases, the second minima just becomes deeper and deeper, and that facilitates the transition from this minimum to the second to the true vacuum by Coleman-DeLucia transition. So if we have first order phase transition, we will have the possibility of primordial black hole formation, as I mentioned. And we will have also a correlated gravitational wave signal from just the bubble walls colliding and also steering the fluid. Of course, here, I mean, because of the fact that the temperature at the end of inflation is 0, there will be no perturbations, no gravitational wave from just radiation or anything like that. But we have still from the collision of bubble walls, we will have gravitational wave radiation. So earlier I had, in this extended hybrid inflationary model, so they have a constant, and they had a m squared phi squared, and this was the term, the term in the potential that would facilitate making inflaton, making a phase transition along the psi direction. And as I mentioned, Liddell and Cortez had worked out the problem. Also, I did some contribution. I noticed that, the prefactor in the nucleation term is they have not taken it to be correct. And by some corrections, I noticed that in this mass range, you would be able to exit the quadratic first slow roll inflation by a first order phase transition. So basically the tensor scalar ratio at the CMB scale is about 1500. NS varies between 0.91 and 0.97. And in the NSR region, you would just go up and then turn right this way. And the least the least R that you would be able to obtain in that model is just the value that you would obtain for m squared phi squared without the vacuum energy V naught. So this got me suspicious that this is just basically the feature of m squared phi squared. So if I can replace m squared phi squared with another model, with a lower just Hubble parameter, then I would be able to just create first order inflationary model that exit inflation with a first order phase transition and create gravitational waves and primordial black holes. So just a review that if a first order phase transition happens at the right after first order phase transition, you would have such a profile of gravitational waves. And FM is just a peak frequency. It has a wedge shape gravitational wave, where FM is the peak frequency, where beta is just the derivative of the Euclidean action with respect to the time. So as you know, even if you have a first order phase transition, you have a Euclidean action and that has to be extremized. And beta is just the time variation of this quantity when the phase transition happens. And the peak frequency is just given by this term. Beta is also a measure of how fast the phase transition takes to complete. And these results are obtained by just simulations that Kosovsky-Turner did in 1992. And Huber and Konstantin did it with more bubbles in 2008. So basically, especially in this falling region, I mean, the Kosovsky-Turner was, the exponent was different, but Huber and Konstantin showed that, I mean, the falling exponent is -1 in 2008 when you consider more bubbles to collide. Beta, as a beta that I introduced, is a measure of how fast the simulations happen. And in order, because simulations are done in a non-expanding background, so beta, I mean, has to be bigger than the Hubble parameter. If you take into account the post-inflationary redshifting, the peak frequency and the amplitude of at the peak frequency would be given by these expressions. So again, beta over HF, and in its inverse to power of 2 appears in just in these expressions. In that model of m squared phi squared, I did the peak frequency, I mean, I computed the peak frequency and the amplitude of the gravitational waves, and I noticed that the gravitational spectra, if first order phase transition happens right after the, just at the end of inflation, this would be in the gigahertz region, where just a probe, Chang-Queen probe of high frequency gravitational wave, basically it's a tabletop experiment, but strangely, even though the signal is not that weak, still, I mean, their sensitivity has not reached this value. If first order phase transition happens after the slow roll violation, in this case, we noticed that I noticed that the power, I mean, the power spectrum for gravitational waves coming from the collision would move to terahertz region. And basically, there is no planned experiment in that region. So the primordial black holes that with such a m squared phi squared model would get produced is just from 1 gram to 15 gram. And such primordial black holes would be evaporated right after inflation. I mean, there is no bound even on them, as much as I know, on their abundance. And therefore, this scenario was not of interest. So my interest was just generating primordial black holes in the mass window of that is still open, 10 to the power of minus 17 to 10 to the power of minus 13. And for that, if you just use the formula Hawking, Moss, and Stewart had obtained, so that would mean that the Hubble parameter at the end of inflation would be something between 10 to the power of minus 26 M Planck to 10 to the power of minus 22 M Planck. So this is extremely low in model of inflation. So if inflation has happened via this mechanism, so basically you wouldn't see any gravitational wave signature at the CMB scales, and you would be able to just, I mean, this would be one signature or lack of signature of the model. But if first order phase transition happens at the end of inflation, from these formula, you would see that the peak frequency would be shifted to the Lisa band. Especially it would be in the 10 to the power of minus 3 to 10 to the power of minus 2 hertz. And the amplitude would be given by 10 to the power of minus 8. Of course, there is this beta over HF, which is how fast the phase transition happens. And this is also important. But without this factor, this would fall into this region. So I assume that in the rolling direction, we want an inflationary model that has such an extremely low value for Hubble parameter. And the only extremely low value for Hubble parameter model with extremely low model of inflation, low scale model of inflation was inflection point inflation, where Alaverdi, Anupam Mazumdar, Carrie Enquist, and some other, and Juan Garcia Bellido in 2006, they had devised the mechanism of inflection point inflation. Especially they had used it for MSSM inflation. So basically for supersymmetric flat directions which are lifted by non-perturbative term, they had shown that such a potential with orange terms would appear. And if tunings of such order where alpha is small is done, then you can reach amplitude of density perturbations of order of 10 to the power of minus 9 and spectral index of 0.965. And for that, alpha has to be non-zero if you want to get this. But the scale of inflation could be also different from MSSM inflation. So basically, the scale of inflation is given by 1/12 of m squared phi naught squared, where phi naught squared is the point where inflection point exists and alpha is equal to 0. So I can just shift it at whatever energy scale that I want. I can tune it to be of order of 10 to the power of minus 26 to 10 to the power of minus 22. And having this low scale of inflation, the number of EFOs in order that you need to solve the problems of standard Big Bang cosmology would reduce to 40. So for just point of concreteness, we in our case, so we assume that HF is a Hubble parameter at the end of inflation is 10 to the power of minus 24 Planck mass. And if you assume that there is instant reheating, then reheating temperature is of order of 10 to the power of 5 GeV, which is bigger than mega electron volt, which is needed for Big Bang nucleosynthesis, quite larger actually. So you can inflate at such low scale, and the resulted reheating temperature could be still high enough for Big Bang nucleosynthesis. So I assumed, so we assumed, me and Abbasal and Javad assumed this kind of rolling direction potential, but we kept the interacting term in the green ones as before. And we initially assumed that V naught is non-zero. So the values that we could tune, that we had to tune our parameters in order to obtain the predictions of inflation compatible with with CMB probes, such as Planck, latest Planck results. So M had to be about 10 to the power of minus 18. Lambda 3 is just basically 10 to the power of minus 13. The cubic term is about 10 to the power of minus 18 M Planck, because it's also massive. Sorry, I have missed the units. And delta phi is actually quite small. It's about 10 to the power of minus 9 M Planck. And that would mean that departure that we would need from inflection point is about 10 to the power of minus 14. Now we assume that V naught, which shifts the rolling direction a bit, is just quite small in comparison with the potential at the end of inflation. So we assume this to be roughly V naught is about 100th of amplitude of the potential at the end of inflation. So if we assume that V naught is about that, the predictions at the CMB scales will just not redshift that much. They're redshifting in, for example, in NS in the 10 to the power of minus 4 with such minus 3 or minus 4. So you can remain within the 2 sigma region of the Planck result. But in the direction that you make a first order phase transition, if you make if you take these values for parameters, lambda prime, alpha 2, gamma, lambda, for example, you can get beta over h of order 150. Of course, in this case, phase transition happens after the termination of slow roll inflation. So basically, the first slow roll parameter becomes 1. But still the inflaton is rolling along phi direction, but still, I mean, at some point, the perpendicular direction, the nucleation rate becomes substantial enough to make a phase transition. And if you compute the peak frequency and the amplitude at the peak frequency, you would see that part of the spectrum would fall in inside the LISA sensitivity band. And you would see both falling and enhancing part of the spectrum. My collaborator, Abbasald, tried to just tune the parameters such that inflation ends with, nucleation, first order phase transition right at phi e, where inflation ends as with the slow roll violation. And he says that only with negative alphas that is possible. But the thing is that beta over h turned out to be huge in this case, and it turns out to be 10 to the power of 14. For this, so that would mean that transition happens about 10 to the power of minus 14 of the Hubble time. And that would mean that the peak frequency would be shifted to basically beyond gigahertz. It's about 10 to the power of 10 hertz, but the amplitude is just getting suppressed because it's related to h over beta to the power of 2. So the intensity for such a phase transition for this example turns out to be small. But in both these two regions, the mass of the black holes that are created is about 10 to the power of minus 13 solar mass black hole. And that's just in the region, in the mass region, which is of interest for us, which was of interest to us. But in the first case, the signal, the primordial black hole, was correlated with the gravitational wave signature 2, which was observable for the LISA experiment. So I don't know, I think I went over time, so I will not, should I go through the conclusions? Do I have time for that?
Very briefly, Amjad, we really are almost out of time here.
PBH in some mass ranges still can be the whole dark matter. And one mechanism for production of, for their production is through the collapse of a large overdensity. Inflation is a prime candidate for generation of such density perturbation. I presented a mechanism for enhancing the amplitude of density perturbation at the relevant scales, which could be embedded in a more fundamental, I mean, in a more formal fundamental framework of extended effective field theory, and because it was modeled through this formalism, it's compatible with the effective field theory criteria. I also suggested a mechanism of primordial black hole formation where inflation ends through a first order phase transition. Such a generation of primordial black holes could be supplemented by a correlated signal in the gravitational wave sector in the LISA region. But that would mean that searches for B mode in the CMB scales would be just fruitless and in vain. And that was it. Thank you very much. Hello? Hello?
Yeah, hi. Okay, sorry, I keep forgetting to unmute. So thanks, Amjad. I don't know if people virtually clap. We're very close to the end of our time. We might be able to entertain one or two very quick questions if anybody has them.
So can you go back to your previous slide, Amjad?
And the conclusion?
Yeah, just the conclusion. So I'm just wondering, so you said the high frequency gravitational wave, I think I missed this. What experiment did you say could detect this high frequency gravitational wave?
So there is a, so I've read that chunking, it's just probe, a tabletop probe, which is just being worked on in Chongqing University at the in China.
Okay.
So the lower frequency sensitivity that they claim is just roughly about 10 to the power of -3, which is quite large, 10 to the power of -3 or -5, I don't know, okay. Which is still larger than the signal that we suggested.
Okay.
Maybe I should also emphasize that this signal, I mean, in this case, you notice that there is one bump. So if it happens, if inflation ends through stochastic resonance, usually the gravitational wave signature that is created has double bump. And maybe the signal, I mean, this way can be, if the whole power spectrum is observed, maybe it can be distinguished from a signal of gravitational wave coming from stochastic resonance.
Okay, thank you.
No problem.
Okay, any other questions? Okay, we're basically out of time. Thanks a lot, Amjad. I mean,